Surprise! You were expecting another piece of paper. Instead, you got a guy dressed up in a red suit. All right, what's going on here? Well, I'm dressed up in a red suit because I'm an electron. Electrons are red. They are. So I'm an electron, and what you need to do is you need to visualize this, okay? You see the floor there? The floor is the south pole of a magnet. You see the ceiling there? The ceiling is the north pole of a magnet. In other words, I am in a magnetic field. The north pole is there, the south pole is there, and there's lines of magnetic flux going straight up and down in this whole room here. You know, magnetism is kind of like electricity in a way. Electricity is electrons going this way, but magnetism is kind of like magnets, or not magnets, but magnetic field lines going straight up and down. So, question for you, you future electrician, you. If I'm an electron, and I'm sitting here, standing here, in the middle of this electric field here, magnetic field, I'm an electron, I got a negative charge. Here I am, in a magnetic field. What happens? I'm pausing because I need you to think about this real hard. You've been reading some stuff in your electrical books, right? Stuff's about magnetic fields, stuff's about electrons, and they're related, right? Okay, I'm an electron, I'm in the magnetic field. What happens? Nothing! Nothing at all happens. I'm just here. Nothing at all happens. But, let's say I'm walking towards you, or not walking. Try to picture me as, like, you know, floating in the air. I don't have feet. I don't need feet. I'm just floating in the air. So I'm the electron floating in the air, and I'm floating towards you. What happens now? I will feel a push. Which way? I will feel a push to my right. Isn't that the goofiest thing in the world? That's what'll happen. If I'm an electron and the magnetic field is going straight from the ceiling to the floor like this, and I'm an electron and I'm walking to the north, I will feel pushed to the east. Unless, of course, I have that completely backwards and I get pushed to the west. But let's just pretend you get pushed to the east. You'll get pushed sideways is the point. You will get pushed sideways. You get pushed to the east. Let's say east. I like east. Okay? That's why I didn't do physics or science. I was like, what, are you kidding me? I'm supposed to believe that? How am I supposed to make sense of that? I'm not doing science. That's, you know. Next question. I'm going this way now. Now which way do I feel pushed? Come on. Well, I also feel pushed to my right. Okay, so if I'm moving along the magnetic field like this, I will feel pushed that way. By the way, if I move straight up or down, I don't feel anything, because then I'm lined up with the magnetic flow. So why does this happen? I really have no clue. It's just an observed fact of nature. If an electron moves through a magnetic field like this, crossing lines of magnetic flux, it will get pushed sideways. Sideways. Okay. Now the good thing about this is we have a way to generate electricity. Think of it this way. Imagine if, instead of me walking towards you and getting pushed sideways, imagine if I filled a big tube, a big, long, wide tube filled with electrons, and I pushed the tube towards you. Every single one of those electrons in there is getting pushed this way. Can you say electrical current going through the wire? So that's how you can generate electrical current. You just take your big old wire, you take a big old, which has electrons in it, I guarantee it if it's metal or whatever. So you've got your wire, and it's lined up this way, and then you make it cross the lines of the magnetic field flux. How? By moving it. And if you push it like this, all the electrons in there get pushed that way, and that's a current. And by the way, if the wire is going back this way, it'll get pushed the other way. That way. Go this way, current goes that way. If I go this way, current goes that way. Okay? Do you like that? I hope you like that. I don't like that. I just know that it's true. You wrap a wire around a nail, you hitch it up to a battery, it's a magnet. It's just true. It's just true. Okay, so with that, we should get to our math lesson. So let's turn that off. Let's turn this on. There we go. Now we're back to normal, right? Intro to sine waves. That's why we've been doing all these vectors for so long. Is because we need to, not today, but you'll see that we need vectors to help us analyze our AC sine waves. So 3 pages to this lecture, 4 parts. Part A is, I already did that really, the thing about electrons and magnetic fields. So you need to write some kind of a summary of what I just said. Put it in your own words. It'd be the best thing. What am I going to say? I'm going to say something like an electron, you could say charge, but I'm going to say an electron moving across lines of magnetic flux, which is just a name for flow. Magnetic flux feels pushed sideways. And there's something called the right-hand rule, which when I was in college back in the 80s, they called it the left-hand rule. So, you know, everything's got to change, right? You can't leave anything the same. You got to tear down the statues, you know. You got to take the left-hand rule and make it a right-hand rule. I don't know why they do these things. So anyway, left-hand rule or right-hand rule. I'm going to do the left-hand rule first because that's the one I don't mix. That's the one I don't screw up. But you know what? I have to turn the camera on again. Uh-oh. Oh, there's the camera again. Okay, maybe I'll do the right hand. So right-hand rule means that if you take the direction of the electron and think of it as moving along your fingers, and then the magnetic flux is going this way, so you curl your fingers in the direction of the flux. So the electron's going this way, but then you curl your fingers in the direction of the magnetic field this way. Then the thumb is telling you which way it's going to get pushed. Okay, so I guess the way I was doing it before, let's see, how was I doing this? See, I was doing a left-hand rule because I was walking into you, the magnetic field was going down, and I was getting pushed to the, that's my right? So see, that's the problem. I was raised with the left-hand rule. These days they call it the right-hand rule, so whatever. So this is probably what I should have done is just, you know, as I move towards you and the magnetic flux is coming this way, I will feel pushed in the direction of the thumb. So you curl your fingers in the direction of the, and you go that way. That's the right-hand rule. You know, it really doesn't matter if you call it left or right. It doesn't matter. The idea is that there's a push sideways. That's what matters. Left-hand rule, right-hand rule, you push sideways. How the heck do I turn this back off? I said off. I said on. Okay, cool. So right-hand rule, left-hand rule, however you want to do it. Use right hand, I guess, and say that fingers in direction of movement, curl in direction of magnetic flux. Your thumb shows which way it's pushed, shows the force it feels. Let's put it that way. It's pushed in the direction of the thumb. So you kind of saw that visual I did. And by the way, in the left-hand rule, I don't think it matters for electric circuits which way you do it. I really don't. Otherwise, they wouldn't have changed it, right? Why would they change such a thing? Oh, I know. I get it. I just figured it out. It's because we used to think in terms of positive charges. So in the old days, when you had a battery, we used to say the current was coming out the positive terminal. And then somebody said, no. The current comes out the negative terminal. So now I know why they had to change it. So if you're a positive charge, you follow the left-hand rule. But if you're a negative charge, you follow the right-hand rule. Okay. Anyway, the important thing was you feel a push, right? And then I showed you that idea of how you can generate electricity. Move a wire through a magnetic field, you can generate a current. Now, the only problem with that is that it's kind of impractical to do it the way I was saying. So think of this as a wire that, you know, it comes back and forth out of the, I'm trying to draw 3D here, it's not working so well. So anyway, just think of that as a wire. So it's coming in and out of the screen here. And if you, again, as you move the wire through the magnetic field, the electrons will flow along the axis of that wire. Well, that's fine, but what happens when you get over to here? Well, are you going to get another magnet? What are you going to do? How big are you going to make your magnet? You can't make your magnet very big, right? It's just you run out of magnets sooner or later. So I've always wanted to build one of these just for fun, just to see how much, how much current I could. Maybe we should do that. Maybe I should do that as a little Hey, anybody want a little extra credit? Talk to me about making a motor, a weird motor. Anyway, to be more practical about it, the way we generate the electricity is not by having a big, giant, long magnet and sliding a wire through it. What we do is we get a semi-big magnet anyway, and we put like a squirrel cage in there. So think of this, I'm trying to draw like kind of like those things that you spin for the lottery, or those things that you spin for the bingo or whatever. So this thing kind of rotates this way. And what's going to happen here? Well, I'm going to call this the 0 degree position. I'm going to call this the 90 degree position. I'm going to get this arrow out of the way. I'm going to call this the 180 degree position. So 0 plus 90 is 90, plus 90 is 180, plus 90. This is the 270 degree position. And then, of course, you're back to 360 degrees, means you're back where you started. And we're going to have the wire, again, so think of these as like, these are all wires that are fastened along the edge of some sort of a hoop or something. And there could be like a bunch of them, right? You can make as many as you want. In fact, usually there's windings involved, not just individual wires, but you get the idea. There's a bunch of wires in there. It's basically spinning around in here. So the advantage is you stay inside the magnetic field. Another advantage is spinning. That's a motion we can get anywhere. You can have squirrels running on wheels to make that motion. You can hitch it up to a windmill to make that motion. You can hitch it up to a water wheel to make that motion. You can hitch it up you can pedal it, for goodness sakes, get a bike and pedal. So there's lots of ways to generate circular motion. So this is actually a very practical solution, sort of. Now, what we need to do, we need to make a table of what's going on. So I'm going to make a table here. I'm going to say, okay, what's going on? Well, the wheel's spinning. So let's just follow like one of these wires around. So when a wire is at 0 degrees, how much current have we got here? Well, remember, this is the lines of magnetic flux. And what I was trying to say is that earlier, when I dressed up in my red Chuck E. Charge suit, was that when the wire goes across lines of magnetic flux, it generates current. Well, here I'm not going across, I'm going with. So actually, I'm generating 0 amps. So I'm going to call this I is for current, right? And I'm going to call this I at position theta. So that's just a little notation there, I at position theta. The current being generated when you're at 0 degrees is 0 amps. Now, if I want to fast forward up to 90 degrees, I'll leave a little space there on purpose. So yeah, when you're at 90 degrees, if you kind of focus on that instant, notice you're crossing like totally perpendicular to the magnetic field lines. You're going to get a lot of current being generated there. So I'm going to call this, I don't know. I don't want to make up a number, so I'll just call it the IP, which stands for I peak. i.e. peak current. You're generating a lot of current when you're going exactly across the lines of flux. So, okay, I'm generating a lot of current. That's cool. Now, when I get back to 180 degrees, well, I'm going with the flux again. That's 0 again. And all of a sudden, I got to get this out of the way. That's pretty good. Okay. Let's say I get down to, after 180, I'm going to go to 270 degrees. Notice at 270 degrees, I'm going across again, but I'm going the other way. And remember, when you go the other way, the flow is the other way. It's going to be the same maximum, but in the other direction. So I'm going to call it negative I sub peak. And then, of course, when you get back to 360 degrees, then it's the same situation as before. You're going with it. And so your current is 0. Now I'm going to start making where can I do this? I'm going to start making a graph of this. I suppose down here would be good. So this is going to be theta going that way. And we're starting at 0 degrees, and going to 360. So I'm going to put 360 over here. Now, if you cut 360 in half, that's 180. And if you cut 180 in half, that's 90. And if you cut 90 in half, that's 45, right? This would be 270, and I'm not going to label everything, but you get the idea. So we've basically got 4 chunks, well, you'll see this in a second. When I'm at 0 degrees, my current is 0 point. When I'm at 90 degrees, I'm at the peak. So this is going to be the peak. And again, I don't want to commit myself to any particular number at the moment, so I'll just say, yeah, it's the peak current. Maybe it's 10 amps, maybe it's 1,000 amps, I don't know. It's the peak, that's what I know, it's the peak. When you get back to 180 degrees, well, you're back to 0. When you get to 270 degrees, now you're at the same peak except negative, except you're down here, negative I peak. So that's at 270 degrees, so I'm trying to make this look pretty good. And then when you get back to 360 degrees, you're back up to 0. Notice this is one full cycle. I've just graphed one full cycle. Cycle meaning that this cage has spun exactly once. The squirrel has run just enough to make this cage spin around just once. Okay, next, I want to talk about 45 degrees. And already, we're going to benefit from our vectors. Our knowledge of vectors. What's going on when I'm at 45 degrees? Well, if I were to zoom in on that, right? Zoom in. Then here's my flux lines going this way, and the electron is kind of going this way. So notice that part of my velocity is going across, but part of my velocity is not, right? I'm moving partly with it and partly without. Can you say components? Vector components? Vector components. Woohoo, woohoo. And so it ends up, to make a long story short, you'd want to take whatever the current is, and you'd want to get its component, you'd have to take this, and this speed is the same whether I'm here or here. It's the same other way. But I'd have to take this and I'd have to multiply it by, I'll call this the x component just for fun. You'd have to multiply it by the cosine of that angle. That angle is 45 degrees, and the cosine of that is 0.707. Hence, when you're at the 45 degree mark, you're at just about 70%, 71% of your peak current. Ain't that something? It all comes from vectors. I always loved that about math. It's so darn consistent. Everything hangs together. It's just cool. The iPad, on the other hand, can be quite challenging sometimes. Look. Let's try this again. All I wanted, no, just, never mind. Okay, so halfway between 90 and 180 would be over here someplace. If you add 45 to 90, you get 135 degrees. And it's also going to be 0.707 I peak. It's all nice and symmetrical. When you get over here, halfway between 180 and 270, take 180, add 45, that's 225 degrees. Now you're at 0.707 I peak, except you're going the other way, so it's negative 0.707 I peak. And the same thing's going to happen over here. Take 270, add 45, you get to 315 degrees, and that's going to be negative 0.707 I peak as well. So now we can finish making our little graph here. So at 45 degrees, I was saying, right there, we're at 0.707 I peak. That's like 7/10 or 0.7 or just somewhere around here someplace. Not all the way up, 0.707 I peak. Let me draw that. 0.707 times I peak. And that was true at 45, and then that was also true over here at 135. Meanwhile, when we crossed the 180, when we came around this way, came around the corner, now we had negative 0.707 I peak, so somewhere like that. And the same will be true when you're halfway between 270 and 360, you'll be at that same point. And now, can you groove on a really cool wave, man? Catch the wave, man, ride it in. I wish I knew some surfer lingo. I could throw it in right here. Ride the wave. I don't know if that's really official surfer lingo. They probably say something much cooler. But anyway, there's a wave. So this is. Oh, what are you? See, this thing does that. It'll like, oh, you have to go like this, and then you have to go like this. And now it'll scroll again. See? Weird. Somebody call that in. Anyway, one full cycle of a of a sine wave. And so that's what, when you generate your electricity this way, spin a turbine in a power plant, whatever, something spinning in a magnetic field, you get your AC waves. And of course it keeps spinning, and so the wave continues forever in both directions. It just goes up, down, up, down, up, down, up, down, up, down, up, down. And actually, I always thought this was kind of an interesting thing to think about. Here's your electrical outlet, right? Tell you what, we'll draw it with a pencil. Here's your electrical outlet, right? It's got those prongs in there, right? So if you plug something into the wall, this is saying that the current is sometimes positive and sometimes it's negative. Doesn't that kind of mean that sometimes it's coming out of the wall and sometimes it goes back into the wall? Somebody asked Don about that. Is that really what's going on? That's what the math says. Math usually doesn't lie. So, weird. It's like, that's how you make AC electricity. It's not just a constant like DC, but it's like a like AC. Yeah. Okay, you. Come on, you. Gee, what's it take? So, where was I on this thing? I think that's really all I got to say right there, right? So now you kind of see where these AC sine waves are coming from. Now you see why AC electricity is these nice smooth waves. So what I'm going to do in part 3 here is I'm going to give you some formulas for these waves. So notice I copied a neater wave down here. And there's some really nifty formulas. There's like, I think about 7 of them that I'm going to throw at you, one at a time. But first of all, let's orient ourselves to this graph here. So this is 0 degrees, right? And the squirrel starts running, and that's when you reach the 90-degree position. You're making peak electricity, and then when you're exactly 180 degrees, you're back to 0 electricity because you're going with the wires moving with the magnetic flux. And then when you get to the bottom, you're generating the max again, except in the opposite direction, which is why we're below the x-axis, we're negative. And then when you get back to where you started, you're back to where you started. And then, of course, the cycle just repeats forever. So that's what's happening here. One thing to note is how we can label our axes. Take one full cycle and call it 360 degrees. One full wave is 360 degrees. And when you take a test on this stuff, I usually have you try to draw a wave. And the way to draw the wave is to make one full cycle go 360 degrees. And then exactly halfway is 180 degrees. Now, if that's exactly halfway, then you expect if the wave started to go up, it's going to cross right here at 180, and and then halfway to 180 is 90, and that's where you hit your peak, and halfway between the 180 and the 360 is 270, and that's where you hit your anti-peak, or whatever you want to call it, your valley. I don't know what you call that. Anti-peak. I like it. So anyway, that's how you draw the darn thing. And then you remember also that this is supposed to be about 0.7 as high, so it's supposed to be 0.7 as high. So this is 0.5, this is 0.75, close enough. Okay, so that's how you draw your wave. Now it turns out there's a really nice formula for that wave. And it goes something like, whoops, where did I put my thing? Oh, darn. Well, it goes something like, where did I put my thing? Here, I don't have my thing. It goes this: take the peak value and multiply it by the sine of the angle. That is big formula number 1. What is I sub theta? It's the equation of this curve right here. It's the equation of this wave. If you plug in the peak value, which is just a constant number, it's like, how high do I go here? Maybe this is 5 amps, I don't know. But whatever your peak value is, you multiply it by the sine of your angle to get the current at that particular moment. So that's like if you're looking at an oscilloscope or something. You say, hey, what's the current at I don't know, 20 degrees? Well, you take your peak value 5 and you multiply it by the sine of 20 degrees, which I think I'll do just for giggles. So I'm taking 5, multiplying it by the sine of 20. I'm in degree mode, that's good. And I'm getting 1.71. Let's see if that works. Where's 20 degrees on this thing? Well, that's 45, right? Here's 90, here's 45. 20 would have to be like, well, a little less than halfway. And see, that's, how am I supposed to read this thing? You know what I should have done? I should have made that a 4. That way this is like 1, 2, 3, 4. Let's just do that. We'll make that a 4. So then I'll plug a 4. Okay. We pause for technical difficulties. Okay, 4 times the sine of 20. Let's do it that way instead. 4 times the sine of 20 is 1.37. So we'll cross that off. 1.37. Okay, so what I'm expecting then is when I come over here to 20 degrees, again, where's 20 degrees? Well, that's 90, that's 45. 20 has to be just a little bit less than half. Here's 20 degrees. Doesn't it look like it comes up? This is 1. Yeah, it looks like it comes up to about 1.37. It really does. So it works, is what I'm trying to say. The formula really, really works. So let me erase some of this stuff because I don't want my graph to be too busy looking. Okay, cool. Yeah, let's get this out of here too. Get out. Oh, scram. Come on. What's it take? Okay, here we go. That's one of your formulas. Now, by the way, this is a current wave. Well, the voltage wave will do exactly the same kind of thing. It's just you would use the peak voltage to get the voltage at any position theta, any position along your wave. So there's 2 formulas, 5 to go. So here's another formula. You see this thing called IRMS. That means root mean square, or it stands for root mean square. And it's kind of like an average effective current. It's not quite the average, but it's close to the, it's not quite the average in a mathematical sense where you add up all the currents and divide by the number of currents. But it's pretty close. It's the average effect of the current in terms of power. A DC current with a value IRMS is the same effect as an AC current with I peak. Okay. Again, I peak is way up here. IRMS is a bit smaller, right? Now here's the thing. There's a really nice formula for RMS current, and it's actually, this is a heck of a coincidence, but it happens to happen right there at the 45-degree mark. And you might remember the cosine of 45 is 0.707. The IRMS value is 0.707 of the peak value. It just happens to be true. So again, RMS is kind of like, let's see, effective. How should I say this? If you had an oscilloscope, the oscilloscope sees the wave just like that. But if you take your ammeter from, I guess I don't say Radio Shack anymore, let's say Walmart. If you take your ammeter from Walmart and you hitch it up to this thing, it's not going to give you the waveform, right? It's just going to give you a steady number, even though it's an AC current. Even though it's an AC current going up and up and down, it's going to give you a steady number. That steady number is the IRMS. Okay, so it's what your meter, not your oscilloscope, but your meter would read the IRMS. Your oscilloscope would show the whole wave, and it would show you the I peak, and it would show you all these things. But the Walmart thing is only going to show you 0.707 I peak. 3 formulas down, except really it's 4 because it's the same thing for voltage. If you want the RMS voltage, then it's 0.707 times the peak voltage. Okay, 4 formulas down, 3 to go. What are the other 3? The other 3 are basically just Ohm's law. We're going to write Ohm's law 3 different times. We're going to write it this way. At any point on the wave, the voltage is equal to the current times the resistance. So that's what the subscript theta is saying. It's saying at some point theta on the wave, any point on the wave, i.e. at any particular, I don't have room over there, so I'll write it over here. i.e. at any particular location theta along the wave, E and I are related by good old Ohm's law. Ohm's law is always true. It holds at every instant. E theta equals I theta times R. Okay, so there's a nice formula. And the other nice thing is you can plug in RMS values, RMS values, and it'll work. And you can plug in peak values, and it'll work. As long as you're plugging in the same kind of thing on both sides, it'll work. So in other words, you can plug in E theta and an I theta. Or if you want, you can plug in an ERMS and an IRMS. Or if you want, you can plug in an E peak and an I peak. As long as you're plugging in the same kind of E and I, Ohm's law is going to work. So there we go. We got 7 nifty formulas. So objective number 1 of our lesson has been finished, and that is to simply kind of show you, back up a little bit, show you how we get AC current waves in the first place. It's because of the way we generate the electricity by having squirrels run in magnetic fields. I showed you where the wave comes from because you just follow the wires around. That's what you get for current. And then I showed you these formulas and this sort of terminology, right? I sub theta, I sub peak, I sub RMS, E sub theta, E sub peak, E sub RMS. Okay, these things are all related by these nifty formulas down here. So that's part 1. Part 2, and this is what your homework's going to be. Part 2 is to basically get used to using these formulas. The more you use them, the more you'll start to remember them, and besides, you need to be able to plug into formulas anyway. So here's what your homework's going to look like. First of all, you'll see where it's going to go. Okay, so you'll notice that we've got all the same formulas here that we just derived on the previous page. 7 formulas, they're all there. And this is how the homework's going to look. It's going to be, this is problem 1 actually, and this is problem 3 from your homework. So this is starting your homework for you. You're given some stuff. You're given a resistance, you're given an angle, you're given in this case, an E sub peak. And then it's like, well, what's that? What's that? What's that? What's that? What's that? So each row is a separate problem. So how do you solve for so many things? Well, the first thing you got to do is get your pencil out because you're going to have to erase. Get your pencil out and say, okay, so for problem 1, what do I know already? I know what the resistance is. So I know what the resistance is. I know what the resistance is. I know what the resistance is. Just circle R anywhere you find it in any of these equations. I know what the theta is. I know what the theta is. I know what the theta is. That's the only place theta shows up. Remember, these are just subscripts, right? They're not theta itself. They're just subscripts. This means E at a position theta. Okay, it's just a subscript. But I also know E sub peak. Where's that? That shows up here. Where else does it show up? Right there and right there. So then you take a look at your equations and you say, well, which equations can I solve? Notice I can't solve this equation yet because there's 2 things we don't know. And I can't solve this equation yet because there's 2 things I don't know. And I can't solve this equation yet because there's 2 things I don't know. Same for this equation. But we're in luck because, look, here's an equation where I can solve for something. I know what this is. I know what this is. I can solve for E sub theta. So I go like this. E sub theta equals, take my peak value, which is where? 12 volts, and multiply it by the sine of theta, which is 4 degrees. And when I do that, 12 times the sine of 4, 12 times the sine of 4, I'm getting, well, I'm getting 0.837 times 10 to the 0. If you're in that scientific mode, like this would be a good assignment to be in the scientific mode, by the way. That would be the shift setup 7 for scientific mode, 3 for 3 sig figs. If you I recommend you do that. It'll be easier on your brain, because when you get the 0.837 times 10 to the 0, I'm sorry. See, I just put my calculator in this mode. What it actually says, if you're in that mode, is it says 8.37 times 10 to the minus 1, because you put it into scientific notation. But you want engineering notation. It says it right there. Engineering notation. You think I'll give you credit if it's not engineering? No. It's got to be engineering notation. So here's this for reference again, right? Remember, we need to have powers of that are 369 or whatever. So you hit your eng button, eng, and now it says 837 times 10 to the minus 3, and then you take the 10 to the minus 3 and you replace it with a little m prefix. So it's 837 millivolts. The 10 to the minus 3 goes away because you're replacing it with the little m. The little m means 10 to the minus 3. So what I just solved for, E sub theta. So that's going to go here, 837 millivolts. That's cool. I'm done with this equation. Maybe I'll cross it off. Let's see. I can solve this equation, right here. That one. And I guess I'll do it down here someplace. So I've got E RMS is equal to 0.707 times E peak. E peak is 12 volts. We just used that before. So that's not hard. Take 0.707 times 12. And we're getting 8.48 times 10 to the 0. So remember, 10 to the 0 just means you can ignore it. Anything to the 0 power is 1 pretty much. So 10 to the 0 is 1. So it's saying 8.48 times 1, which means you don't need a prefix at all. It's 8.48 volts. I should put the V for volts. Okay, so make sure you're clear about your prefixes. That's a millivolt, that's a volt. Cool, I'm done with that equation. Let's see, I can go to this equation now. E sub P equals I sub P times R. Okay, let's get a look at this one. E sub P is, we know that's 12 volts. I sub P is, wouldn't we like to know? And the R, get it from here, is 100 ohms. So how do you solve for the I sub P? You have to say, well, I don't want it to multiply 100, so divide both sides by 100. And 12 divided by 100, if you're in scientific mode, it's going to tell you 1.20 times 10 to the minus 1. And if you hit your eng button, it's going to say 120 times 10 to the minus 3. 10 to the minus 3 goes out, milli goes in. We were solving for a current, so it's going to be a milliamps. So what did I just solve for? I sub P, and that's 120 milliamps. That goes here. Okay. Double checking myself. That's what I got. Yep. That's what I got. Yep. That's what I got. Yep. Cool. I'm on a roll here, folks. What else can we do? Well, I guess I just used that equation, right? And by this time, it's like, okay, I've solved for some more stuff here. Maybe I should update up here. I solved for E sub theta, which means I know what that is. So notice right away, I can solve this equation for I theta. E sub theta is 837 millivolts equals I sub theta times R is 100. Oops. R is 100. So I can divide both sides by 100. So 837 milli, which means 10 to the minus 3. So remember how we used to enter this? We'd enter 837, we'd hit the times 10 to the x button, we'd hit the minus button and the 3 button. So that's 837 times 10 to the minus 3, and then I say divide by 100 equals, and my calculator is now saying 8.37 times 10 to the minus 3, which is great. I don't even have to hit the eng button. It's milli again. 8.37 milli. What did I solve for? I sub theta. 8.37 milliamps. By the way, E is always volts, I is always amps. No matter what kind of E it is, no matter what kind of I it is, E is always volts or millivolts or whatever. I is always amps or milliamps or whatever. One more, I need my IRMS, that's this formula. So I'm going to come down here and I say, okay, IRMS equals 0.707 times I sub P. I'm just looking at this formula up here. So all I got to do is take my 0.707 times my peak current, which is 120 milliamps. 120 times 10 to the minus 3 amps. 120, 707, and this comes out to be 84.8 after I hit eng button and all that stuff. 84.8 times 10 to the minus 3. Again, this becomes a milliamp. And that goes here. 84.8 milliamps. okay, can you see why I did it in pencil? I did it in pencil because now I want to erase all that stuff so I can work on my next problem, right? Come on. Okay, there we go. I want to work. What? Every time I use that, it's gonna. Sheesh. That's a bug, man. That's a real bug. Okay, let's go like this. Okay, so if I go like this and I delete, now I can't scroll. Oh, I can scroll now. All right, it's only half a bug. So, what do you say? You want to try this yourself? You want to try problem number 3? That would be a darn fine idea because you got more problems to do for homework. Just try number 3 yourself. See if you get stuck, because this is how you learn stuff. This is power learning right there. It's when you try something, get stuck, and then get unstuck. That's when the learning happens. You send those extra impulses down your brain wires. It makes them real thick. That's science, by the way. That's not just me. So if you get stuck and then unstuck, hopefully soon, it's good for you. So anyway, try number 3. Pause the tape. Pause the whatever. Come on back. I'm going to get out my pencil. This time I'm going to use a brown pencil. So what do we got here? I know what the R is. So again, I can circle all these R's. I know what the theta is. So again, I can circle these thetas. And this time what I know is the ERMS, which is this one. And it also shows up here. Okay, so that's the information I start with. Take a quick look at these equations, say which one's ready to solve. This one's ready to solve because it only has one unknown in it. So I'm going to do this one first. Maybe I'll put a little 1 next to it. I'm going to do that one first. By the way, you might have done this one first. That's fine. I'll be doing that one in a second. So anyway, I'm going to do this one first. So it's, again, just to copy the equation. It says ERMS is equal to 0.707 times the peak value. What we have here is an ERMS of 14 kilovolts. And maybe just to be explicit, that's how I enter kilo on my calculator. I cash in the K for a 10 to the 3. 0.707 times E sub peak. This is what I'm trying to solve for. So I have to divide both sides by the 0.707 here. And let's see what I get here. I get, let's see, 14 times 10 to the 3 power equals, divided by 0.707 equals, oh, okay. That's wrong. Let me try that again. 14 times 10 to the 3 power. I hit the equals just because. Divided by 0.707 equals. Okay, that's better. Hit my eng button and all that. I'm getting 19.8 times 10 to the 3 is equal to my E sub P. So again, the 10 to the 3 becomes a kilo. 10 to the 3 goes away and you get kilo. It's voltage E, so it's kilovolts. 19.8 kilovolts, that's my E sub P. Try to make it look like a 19.8, shall we? 19.8 kilovolts. Cool. Let's solve that one next, because notice it's ripe. It's only one thing we don't know in that equation. So my second thing I'm going to do is I'm going to do this one. ERMS is equal to IRMS times the resistance. The ERMS, again, is 14 kilovolts, which I will enter this way. And that's equal to the IRMS, which is what I'm solving for, times the resistance, which in this case is big, 120 mega ohms. Mega means 10 to the 6th. So notice what I got to do here. If I want to get my IRMS by itself, I'm going to have to divide this on both sides. And so I've got IRMS is equal to, all right, our survey said 14 times 10 to the 3 is equal to, divided by 120 times 10 to the 6 is equal to, hit my eng button, and I'm getting a 117 times 10 to the minus 6. So you have to remember what minus 6 stands for. So we've got this nifty little table down here to help us remember. Micro. So 10 to the minus 6 goes out, micro goes in, and we're talking about current here, so it's amps. Fill in the table. I sub RMS is equal to, over here, 117 microamps. Does that what I got before? Oh, good. I like when that happens. Okay, 2 down, 3 to go. Oh boy, what am I going to do here? Come back up to this one. So I guess we just solved this one. Right? And I suppose I could update my table a little bit because, or update my circling up here because we've solved for E sub p, so I can circle that and I can circle that. And we've solved for IRMS, which means I can circle that. Yep. Cool. Maybe I'll enter phase 2 using green. Phase 2. So I'm just looking over here and I'm saying, there's a nice equation. This will be my equation 3. It says E theta is equal to E peak times the sine of theta. This one. I know 2 things, so I can solve for the leftover. So I copied my formula down first. So what is E sub peak? It's over here. It's 19.8. Times 10 to the 3, I guess. Kilo means 10 to the 3. So it's that many volts times the sine of theta is 6 degrees this time. Let's see what I get this time. 19.8 times 10 to the 3 equals times the sine of 6 degrees equals, and I'm getting actually 2.07, and it's times 10 to the 3. So it's 2.07 kilovolts is my E sub theta. 2.07 kilovolts. We're rocking, man. We're rocking. So that one's done. Oh, here's an equation I can solve. I notice this only has one thing left in it, so let's solve for that. Number 4. So the equation I'm looking at is, maybe I should shrink this. The equation I'm looking at is IRMS is equal to 0.707 times the I peak. And I know what the IRMS is. It's 117 times 10 to the minus 6. Micro is 10 to the minus 6. Equals 0.707 times, well, looks like I'm going to solve for that. 0.707 I peak. To get the I peak by itself, you have to cancel off the 0.707 because those two are multiplied. You have to cancel it off. So 117 times 10 to the minus 6. Is being divided by a 0.707, and that's going to give me, actually, a 165 times 10 to the minus 6. So my peak value is 165 micro. Making sure that's what I got before. Yep, 165 microamps. And then finally, to get the I sub theta, well, here's the formula for I sub theta. It says take your I sub peak times it by your sine theta. Okay, so my I sub peak, where is that? That's the 165 microamps times the minus 6 for micro times the sine of 6 degrees, I guess. So what do I got here? I got 165 times 10 to the, didn't I just do this? No, I guess I didn't. Okay, 165 times 10 to the minus 6 is equal to, I have to multiply that by the sine of 6, hit the edge button, 17.2 times 10 to the minus 6. So this is 17.2 micro amps, and I'll expand that back out for you so you can see. There's our nice, that's a micro, there's our nice set of answers for that one. Double, triple, fourple checking. Yes, that matches what I had before. Groovy. Okay, that's 2 down. I think you got like 6 more of these things to do on your homework. So of course, it's attached in the description of the video below. Have at and enjoy.